proton to generate this resonance stabilized system, okay? But if I go back here, notice that in this reaction, there's two steps. The first one is using the base, which gets you to the deprotonate version, but in order for me to deprotonate this position back at the very end, I'm gonna add acid. So we always see a 1-2 step process because in the end, I'm gonna have to protonate that enolate that's formed in the last step. So that last acid permits me just to protonate this species here to give me the final product. Okay. And again, this just shows the differences between the clays and an aldol. The aldol stops at the tetrahedron intermediate, which I protonate to make the beta hydroxy system. Whereas because we have a good leaving group here in the Claisen reaction, this eliminates to regenerate the carbonyl. Okay, so this is the only thing mechanistically that's distinguishing between these two reactions, is basically how the nucleophile reacts with the various carbonyls. Some carbonyls, the aldehydes and ketones, only do nucleophilic addition, whereas the carboxylic acid family does addition followed by elimination. So overall, that's substitution. Okay.
Why is it more stable to have that negative charge on the final structure?
Well, again, my point here is the final product is this guy. So yes, the driving force is to go to the negative system, but in order to isolate, I have to basically, and this is just something that one does, is I have to add acid to protonate that position so that the final product is neutral. Okay, so yes, under the reaction conditions in the first step, the driving force is deprotonation to generate this guy. Once the reaction's done and I'm ready to work it up, I'm going to quench it with acid just to protonate this position here to give me the final product, which is neutral. Okay, so again, I'm trying to explain why there's two above the arrow in this reaction. Above this reaction, you'll see step 1 followed by step 2. The step 2 is the acid phase, which is basically protonating the final step enolate. Okay? And so as I pointed out to you, you must have an alpha hydrogen at this position. If I notice I have 2 carbons here and I still have a methine, so I could still deprotonate that and drive that reaction. If this was 3 alkyl groups or something else, it would not go to completion. Okay, so again, in that last step, you have to have the alpha position deprotonate. Okay, so this system, what I'm sharing with you here is this system would not undergo the Claisen reaction. So I ask you guys to try this mechanistically and convince yourself that the reason for that is in that final step, I don't have an alpha proton to drive that reaction. Okay? So all of you guys should be able to see why this does not do the Claisen, this ester. So in general, if you only have 1 proton on the alpha carbon, the reaction doesn't work. You have to have at least 2 or 3 alpha hydrogens in order for the Claisen reaction to work. Okay, recognize why. Well, if I go back to the mechanism, the first one generates the nucleophile, right? So if these 2 R groups, if this was a methine here, I would have 2 R groups here, and I would have 2 R groups here, right? So I basically have lost the only methane I had in the first step in this nucleophilic addition. So now I have 2 R groups here and here. Once this is regenerate, both of these are R groups here. If they're both R groups, then I have no proton to abstract here if they're both R groups. So again, the requirement for this reaction is that the ester must have, your starting ester must have 2 or 3 alpha hydrogens. If it only has 1 or 0, you get nothing. Okay? Now, just like aldehydes that can do an intramolecular aldol, esters can also do an intramolecular reaction. This is called the Dieckmann condensation. So for whatever reason, traditionally, the intramolecular claisen is not called an intramolecular claisen. Instead, it's called a deacon. It's very similar, again, to what we saw with aldehydes and ketones, and also very similar mechanistically. It's no difference with the claisen reaction. Again, the driving force for this reaction is the formation of 5 and 6 member rings. Okay, so if I have the possibility to form either a 5 or a 6, it will do so. So here I have a diester, and if I deprotonate this position here, this forms a nucleophile, right? So if I count 1, 2, 3, 4, 5, I have the possibility of this adding to this double bond to make a 5-member ring, and it will. So here it is, and because I have a good leaving group in the ester, I will regenerate the carbonyl through elimination to give me this beta keto ester. Now recognize I still have that driving force. I still have an alpha proton between the beta keto ester that I must abstract in order to get that. The final step is acidification to generate this product. Okay, so again, it's a 1-2 step process. The first step is treating this with sodium methoxide. That stops here. The second step is to add acid to neutralize it to get the final product. Okay. Are there cross-claisen reactions? Yes, and it's the same type of approach. Obviously, one approach is to identify an ester that can only function as electrophile because it has no alpha protons. So here's a case of ethyl benzoate. Again, this carbon here has no protons. So because there's no protons on it, I don't have a nucleophile that can be formed. Consequently, ethyl benzoate can only function as the electrophile in this reaction. Consequently, what we're going to do with sodium methoxide here is deprotonate this alpha position, make a nucleophile. Once I make that nucleophile, this guy can react with this carbonyl to make 60% of this product. Okay, well, one point, why isn't this higher? Well, part of the reason is, again, ethyl acetate can also react with this self. Okay, so again, I'm seeing 60% of this, but I'm sure there's some self-condensation of this guy here. Here's another example of that. Okay, this is diethyl carbonate. Carbonate is a carbonyl that has 2 oxygens on each side. So if a carbonyl only has 1 oxygen, that's called an ester. But if a carbonyl has 2 oxygens, this is a class of molecules called carbonates. And so we could use carbonates because by default, since we have oxygens at the alpha position, there's no hydrogens on a carbon, so we can't deprotonate. So consequently, carbonate can only function as electrophile. So then I'm going to try to identify the nucleophile. The nucleophile here is one of these protons on the alpha position of this ester. So if I deprotonate this, obviously that forms a nucleophile that's going to react with this carbonate as an electrophile through nucleophilic addition followed by elimination to give me now, instead of in this case, if you use carbonate, rather than get a beta keto ester, notice you get malanates, diethyl malanates. So this is another example of making substituted malonic esters. Okay. So these are a couple of examples from your textbook. Yes, I believe they're from your textbook. Your textbook shows these 2 examples. Okay, so here's a cross-claisen. Obviously, this guy has no alpha proton here, so the only alpha proton I have is this guy here. Okay, so if I use sodium methoxide, I'm going to generate that enolate. That enolate is going to attack that carbonyl. Again, it's going to go through the nucleophilic addition stage to the tetrahedral intermediate. But because I have an ester, it collapses to eliminate the leaving group to regenerate the carbonyl. So notice I generate a beta keto ester. Is there still enolizable protons at the end? Yes. Recognize that this position has 2 protons. Again, the reaction is restricted if I only had 1 alpha proton. So since I have 2 alpha protons, the reaction will proceed. And again, I need the second step to basically protonate that position here in the very end to get this. So notice you always have the 1 and the 2. Okay? Here's another example of that. This is another example of a Claisen reaction where this ester is only an electrophile because it has no alpha positions here. 1, 2, and then the double bond. That's a carbon with 4 lines, so there's no hydrogens on it. Okay, so no alpha protons there. Consequently, this is only the electrophile. Here I have a ester that has 2 methylines here. Okay, or I'm sorry, 1 methylene with 2 hydrogens. So I have a carbon with 2 hydrogens. This should be able to undergo the Claisen reaction, in which I deprotonate this guy attacks, and again, eventually we will protonate the beta keto ester portion of it and get to that. Okay. So I apologize. I'm not going to use a document camera for today. One of the things I'm going to try to do in a few minutes during office hours, when we have that 5-minute break,